Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE, and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth, and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series in electricity and magnetism. We are discussing the concepts related to magnetism and magnetic field in this part of the lecture series. In today's lecture also we are going to continue with the magnetic field produced by various current carrying elements. So, before we start this lecture, let us see the session outline of today's lecture. In this session, we are going to see Ampere's circuital law, applications of Ampere's law, and we are going to use it for finding the B due to a solenoid and a toroid. Also, we are going to learn the properties of the magnetic field B, the curl and divergence of the magnetic field B, and also a new term called magnetic vector potential. So, we have got these topics to be covered in this lecture. Let us first start with the concept of Ampere's circuital law. What is it? Why it is called a circuital law? So, let us see the circuital law with the diagram. It was first proposed by Henri Marie Ampere, a French scientist. He has established a mathematical relation between the current distribution and the magnetic field produced by them. The Ampere circuital law is a mathematical tool which makes the method of finding the magnetic field due to various current elements easy. We need not use Biot-Savart law for every case. It involves lot of geometrical considerations and also the integration. Sometimes the steps would be little tedious, but this Ampere circuital law becomes handy in doing that kind of calculations to find the magnetic field due to various current elements. So, let us first learn what is the Ampere circuital law and how it is to be used effectively. So, let us see what is the law. The line integral B dot dl, here B and dl are vectors. B is the magnetic field, the dl is the small length. So, they are vectors, and this line integral for a closed curve is equal to mu naught times the net current through the area bounded by the curve. And in the explanation with words it is not fully understood, but in the mathematical expression like this the Ampere circuital law is understood in a better way. So, here we have the line integral B dot dl. Why this circle is there in the integral? We have come across this integral notation in Gauss law when we learnt the applications of Gauss law and all the related concepts in electrostatics. We have come across the same circle. There we have used it for a closed integral over a closed surface. Suppose there is a volume it has got a surface, closed surface, it is covering it fully. So, for such kind of surfaces we used, the circle shows it is a closed area, and here it is a closed line, that means it is a loop. So, this circle defines that it is considered for a closed loop, and that line integral is equal to mu naught times I net. Why the net is written here? It is the total current, and when we say total current we have to be little careful. So, I would like to explain with this diagram here. We consider as Ampere's loop, the blue line that I have shown is the Ampere's loop, and it covers some of the current elements. I1 is one current carrying wire, I2 carries current downward, I3 carries upward. So, all are in different direction, right, and due to these elements together what is the magnetic field at this point. So, we need to consider the small elemental section dl of this loop. This loop is a closed loop, right, and B is the magnetic field. So, that angle we need to consider because it is a vector form, we have the cos theta here. So, that theta is the angle between the dl element and the magnetic field B. So, this is theta. In scalar form, if you want to write what is that same expression, it is B dl cos theta, which is equal to mu naught I net. And about I net we have to be little cautious. The current is going upward, downward and all that. So, we have to take the upward direction as positive, downward direction as negative when we consider the sense of the loop that we consider. So, here the net current is I1, the I net if you want to write mu naught I net is I1 is taken positive, I2 is negative. So, plus minus I2 and plus I3 is also taken positive. So, this is how we need to find out the net current. It is the algebraic sum with plus and minus signs which take care of the direction. So, having got the mathematical expression for Ampere's circuital law, how it is to be used for finding the magnetic field produced by various current elements. Shall we choose the known current element like a straight wire and apply Ampere's circuital law and check whether it gives us the known answer. What is the magnetic field produced by a straight wire? B is the magnetic field, which is equal to mu naught I divided by 2 pi A. A is the distance between the wire and the point where we consider. The same approach if we have it here, when we use the Ampere's circuital law, we have to get the same expression. Shall we check that? The magnetic field around a current carrying straight wire is shown here, and if you place a compass, magnetic compass or needle, this is how the alignment will happen, and we have to consider a small elemental part of the Ampere's circuital loop. So, we will do that for a straight wire. We can start with the Ampere's circuital law in the vector form, and it is written further in the scalar form. And what about the angle theta? Theta is 0. How it is 0? I would like to mark and show you that. Let us take this point. At this point the magnetic field will be like this, and the dl vector is also like in the same direction, the small elemental part. So, B and dl, the angle between them is 0. So, cos 0 becomes 1, and B is a constant because we have considered the Ampere's loop as a circle itself, which coincides with the magnetic field. So, B is a constant, integral dl is the circumference 2 pi A. So, the further simplification gives us the known result, B is equal to mu naught I divided by 2 pi A. I would like to bring it to your mind, if you do not use this Ampere's law and start with Biot-Savart law, which that itself has been done in one of the episodes, we have to do lots of calculations, right, consider triangles, the geometry, and then do the integration, all that. But here in simple steps, see, in one slide itself with few steps we have arrived at the famous expression for magnetic field due to the current carrying straight wire. Same answer we have got. So, the Ampere's circuital law is a powerful tool in finding the magnetic field. Only thing is we have to be cleverly substituting for the terms, the closed loop and also the calculation of I net, both have to be done carefully. Now, we will take some of the special current carrying elements. Coil also we can take and do, and extended coil which is called as solenoid. Coil is the one which has got winding at the same place. See, if you say a coil, it has got number of turns, number of windings in the same place over and over. But solenoid is an extended coil. What is an extended coil? It spreads over a space. The number of turns is wound in a helical way. So, that is called solenoid. So, we will take up such a little complex current arrangement like a solenoid and extended coil, and because we have got a very easy tool, Ampere's circuital law, which makes the calculations easy. So, we will balance it with a little complex current elements like solenoid and try to use the Ampere's circuital law for finding the magnetic field. Shall we take it up for our discussion? So, what is a solenoid? As I have said, solenoid is a long wire wound in the form of a helix. It is also called an extended coil. With this configuration, a uniform magnetic field can be produced in the space. Space here refers the interior surrounded by the turns of the wire when the solenoid carries a current. When the turns are closely spaced, each can be approximated as a current carrying circular loop, and the net magnetic field is the vector sum of the fields resulting from all the turns. Hope a kind of visualization will enhance your understanding of the solenoid. So, have this visual in front of you. So, I have shown the helical coil and how it produces magnetic field using right hand thumb rule. If you hold each turn, the vector summation will be like this for the magnetic field. For each turn it is circular, but at the center it gets vectorially added, and this is for a loosely wound coil, and here it is shown for a tightly wound coil. All the turns are very close to each other. So, are you not relating this one to a bar magnet? So, a solenoid also acts as a bar magnet. A coil acts as a bar magnet, a solenoid very much acts as a bar magnet. So, shall we take up this solenoid and use the Ampere's circuital law for finding the magnetic field produced by this solenoid, especially at the interior part. So, how the coil arrangement will be? When we take a cross sectional view, so this is how the current will be flowing. These dots show the current comes up outwards from this, and here this cross marks show the current is going into the page. How it will be? See, this is the 3-dimensional view. The current goes like this. For each turn the current goes, and for each turn it goes like this. So, we do not want those current elements in between, because it will be disturbing the other considerations. So, we have the current elements shown here, and this is the Ampere's loop, this loop which has portions, 4 portions. It is a rectangular loop, 4 portions it has, 1, 2, 3 and 4. The length of the closed loop, the Ampere's loop, is L, the width is marked here as W. The Ampere's path could be a rectangular closed path with section 1, 2, 3 and 4. In sections 2 and 4, here they are 2 and 4, and the B and DL magnetic field produced by this is shown here upwards, the blue line. The B and DL is along this. I would like to mark that this is the direction of DL here in this portion. For 4 also, this is the direction of DL. the current loop has got these directions. So, dl, and this is the direction of B, the direction of B here, this is dl, and here this is the direction of B and the dl, they are perpendicular to each other. So, what is B dot dl? It is 0 because they are vectors, B and dl are vectors, they are perpendicular to each other. So, the dot product will become 0. Why it is so? So, it is B dl cos 90. Cos 90 is 0 because this is 0, the entire term becomes 0. In section 3, B is 0, where is 3? 3 is outside. So, this is not the interior, it is the exterior portion. So, it is outside, the B is 0. So, this segment, the B dot dl is 0, and B dot dl will have a value only for the section 1. So, here we have the section, only in the interior section we will have a value due to the section 2, 3 and 4, the value of B dot dl is 0. So, let us start with the Ampere's circuital law. Let us start with the Ampere's circuital law, which is written here, and this is for the term that is considered inside. I have included this number. This number n is the number of turns of the coil enclosed by the first section. Shall we have a look at the diagram? See, this is the first section. It includes these turns, right, which are included. These outside turns are not considered, only the terms considered covered by this section 1, that is shown here as the n. And we write what is this B dot dl for the section 1, 2, 3 and 4, but we know the section 2, 3 and 4, they do not contribute, they all become 0. So, they are not contributing anything, it is the first section only contributing, and for that section the angle is 0. So, cos 0 becomes 1. I think it is a easy integration to understand. The integral dl is taken as the length L, which is marked in the earlier diagram, and bring this L here to the denominator. So, this term is called the number of turns per unit length. This is the number of turns enclosed by the section and L is the length. So, that is marked here as small n. N is the number of turns per unit length of the solenoid. This is the geometrical arrangement. So, B depends on the number of turns per unit length of the solenoid and the current the wire carries. And of course, this mu naught comes into the picture because the solenoid would be producing magnetic field in its interior, but the interior space is of free space. So, that is the mu naught, which is the permeability of free space. So, it depends on the current and the number of turns, only these two quantities. Look at the way in which we have arrived at this result. If you use the good old Biot-Savart law, the integration would have become very tedious. So, lots of calculations have been avoided by using Ampere's circuital law. We can take up such cases for finding the magnetic field. We can have one more geometrical arrangement, that is called a toroid. What is a toroid? Toroid is a device often used to create an almost uniform magnetic field in some enclosed area. The device consists of a conducting wire wrapped around a ring. A ring is called a torus, made of a non-conducting material. So, this we call it as a torus or a core. So, here we have the core and it is the coil is wrapped or it is wound around it, and if you cut here and extend it, it will become a solenoid again. What is the toroid? We need not consider that it is a specially made one. See here, if you have an extended coil which is a solenoid, connect them like this, make it into a circle. So, that is a toroid. So, if you extend a toroid and it becomes a solenoid which is brought with the two ends closer, is called a toroid. But for a toroid also we have to pass the current through one end of the wire and take the current through the other end. So, that is also marked here. See this is important. The current enters through this section, through this wire, and it is encircling this base which is a torus, and it is coming out. We call this as a core, right. And when we say it is a core, one geometrical shape comes to our mind. It is nothing but a donut or an annular ring, a tenicoid, the ring we have on which the coils are wrapped. So, that is also an example for a toroid. So, toroid is a common shape, but here the magnetic field is produced in a circular manner. See this, the magnetic field is in a circular manner. It does not come out from one point and end in another point. If you compare this arrangement with a solenoid, for a solenoid how it is existing? See, for a solenoid it appears as if the magnetic field is coming out from one end and it is ending in another end like this. But as far as a toroid is concerned, almost the magnetic field starts and ends at the same point. So, where do we have the north pole and south pole? We do not have anything. A single point itself is acting as a north and south pole, but when we break open, when we cut it here, one end becomes north pole, another end becomes south pole. There is the intense magnetic field existing between the two ends. We are going to get an expression for the magnetic field for this kind of arrangement, which is called a toroid, using Ampere's circuital law. So, this is how we start the derivations. For a toroid having n closely spaced turns of wire, we can get the expression for the magnetic field in the region occupied by the torus. A distance r from the center, it is also marked here in the diagram. R is the radius of the torus, the core. Let us start with the Ampere's law, which is called Ampere's circuital law, like this: closed integral B dot dl is equal to mu naught n I. Here n is the entire number of turns. And how do we consider the Ampere's loop? See here, the Ampere loop is already marked in blue. We go around the core of the torus, and that loop only has got the small r as the radius, and the current elements are all shown here. The current comes out from this point, outer point, and the current is going in, and we would like to find out, because this loop includes all these current elements. So, the entire number of turns is total number of turns is considered, and here also the angle between the magnetic field is like this, the dl is also like this, magnetic field B, the elemental length of the circuit loop is dl, they both are in the same direction. So, cos 0 it is, the cos 0 will become 1. So, the steps becomes very easy. The further simplifications give us the expression for magnetic field produced by a toroid. Here also we need to integrate dl, here dl is the circumference of the loop that we have considered, and when we bring this 2 pi r, which is circumference, to the denominator, we finally get the expression for the magnetic field produced by a toroid. And what about the application of this toroid? These kind of shapes, toroids, are used for trapping the charged materials. In the upcoming lectures, we are going to learn about the force that is acting on the charges when they move in magnetic field. So, at that time we will have to use this toroid field produced by a toroid and how the charges could be trapped inside. So, at that time once again we will revisit the concept of toroid and the magnetic field produced by it. The key point here is the magnetic field is complete circle, it is a loop. So, we do not have north pole, south pole kind of thing. Any point that you consider, if you cut here and try to separate it like this, because the magnetic field is in this direction, this is becoming north pole and this will become south pole, like that it goes, and here it is shown. Suppose if you cut it here, the magnetic field here it is coming out and here it is ending. So, this is north pole and this part is south pole. So, any section will have such north and south pole existing at the point where we consider a cut or a separation. So, we have a magnetic field as a closed loop or closed loop kind of arrangement, a circle, especially in the case of a toroid, which has got lots of application to produce magnetic field around some of the objects, and we can develop the concepts of magnetic field further, but we need to learn some of the basic properties of magnetic field. We have learnt how the magnetic field magnitude is calculated using Biot-Savart law and Ampere circuital law, and the direction using right hand thumb rule and the other related methods. And what about the property of the magnetic field? So, let us quickly run through some of the important properties that will help us to have the understanding, basic understanding of magnetism. So, these are the properties of magnetic field. The properties of magnetic field lines can be summarized by these rules. Magnetic field lines are closed lines, they do not have north and south pole if it is considered as a loop. There is no monopole in magnetism. I would like to explain a bit about this. In the case of electrostatics, we have one charge as positive and another charge as negative, two sets of charges. But in the case of magnetism, we have north pole and south pole, right, in the natural magnetism also. But when we try to separate one pole, it is not possible. The other pole also will coexist, it will get created. So, monopole concept is not there. Because of that, the concepts are totally different in the case of magnetism. Some of the similarities we have in considering the directions and all that, but as far as the monopole concept is concerned, the magnetism is totally a different case than that of the electricity or electrostatics. So, we will learn more about it as we proceed in learning the properties. The direction of the magnetic field is the tangent to the field line at any point in space. The strength of the field is proportional to the closeness of the lines. So, the length of the lines are packed, higher is the magnetic field, the magnitude wise. So, these are some of the key points. I would like to highlight upon the two important things. One is the magnetic lines are closed lines and we do not have monopole. These are the key points to be kept in mind as far as the magnetism concepts are concerned. Now, there are few more technical terms that we quickly run through. As there is no monopole in magnetism, the magnetic field B is solenoidal. What is the meaning of solenoidal? If you consider a field, whatever is entering is going to come out. In the case of electrostatics, there is a positive charge from which the electric fields are coming out, like that we have learnt. But in the case of magnetism, as there is no monopole, whatever magnetic field is entering a region will definitely come through the other side, because we do not have any source or sink, north or south pole is not there. So, such a field is called a solenoidal field in mathematics. So, that is the meaning of this. So, for such fields, the divergence of that, the div of B is 0. What is div? We have a del operator here. I hope these are all very familiar terms. So, del dot B is 0 because it is a solenoidal one. So, the above is the differential form of Gauss law in magnetism. And what about the integral form? The integral form of Gauss law in magnetism could be given as closed integral B dot ds is equal to 0. Here S is the area now. So, it is a closed area. If you consider the magnetic flux over a closed area B dot ds, it will be 0 because whatever field is entering will be coming out. So, that is called solenoidal. The curl of B could also be explained as the magnetic field B is a vector quantity. There exists a mathematical composition that it could be written as the curl of a vector quantity. any vector quantity, we could write that vector quantity as a curl of another quantity. So, here A is another vector quantity. The A is called magnetic vector potential, because this is written as an operator along with an operator. So, B is the magnetic field, A is called the vector potential of the magnetic field. This is from the pure mathematical composition. The magnetic field B could also be written as the gradient of a scalar as follows. So, this way also the gradient of a scalar is also a vector. So, B could also be written in terms of a term called phi m. So, here the phi m is called the magnetic scalar potential. I have quickly mentioned the two terms. There are two potentials, vector and scalar potential in magnetism. We will learn more about them in the upcoming lectures. It is time for us to go for the summary of today's lecture. In this lecture, we have seen Ampere's circuital law, applications of Ampere's law, in which we have calculated the magnetic field due to a solenoid and a toroid. Also, we have seen the properties of the magnetic field B, the meaning of curl of the magnetic field B and the dive of the magnetic field B, and also the terms vector potential and scalar potential of the magnetic field B. Before we wind up this lecture, let us test our understanding by answering these questions. State Ampere's circuital law. Using Ampere's circuital law, find the magnetic field due to a straight current carrying wire. Apply Ampere's circuital law to find the magnetic field produced by a solenoid and also a toroid. Mention the properties of magnetic field B. What are scalar and vector potentials of magnetic field B? With this, I would like to wind up this lecture. See you in other lectures with the concepts related to magnetism. Thank you for watching this program.